My name is Ted Smith. I am the field applications engineer for the sensors product line here at MPS. Today we'll be talking about environmental errors and differential techniques that we use to minimize or eliminate those errors in magnetic sensing. So the outline will look something like this. We'll go through a little bit of magnetic sensing basics, specifically accuracy in magnetic sensing. That's the important thrust of what we're talking about. We'll discuss some sources of interference and their relative field strength and effects. And then we'll get into what differential sensing is, how it's architected, and how it's designed to reduce or eliminate those external sources of interference. Go through a couple of examples, and then I'll address any questions. I will do a Q&A session. So to start with basic accuracy in magnetic sensing, we have three fundamental categories for magnetic sensing. And when I talk about magnetic sensing here, I'm talking specifically about position sensing, magnetic position or angle sensing, and magnetic current sensing. Those are the two types of products that MPS makes, and so that's kind of what we specialize here. But in both, there are three categories. There's the systematic errors that can be calibrated out. There are random errors that can be essentially dealt with by filtering. And then there's the external influence. So this is things that, for example, permanent magnets or high current conductors that are nearby. And for those, we typically have in the past used shields or shunts, but differential technique is a lower cost and requires no extra space. So that's what we'll be focused on today. Let's first take a look at these systematic error sources. So essentially three systematic error sources. These can be, again, calibrated. We are looking at integral nonlinearity. This is INL that is intrinsic to the part. Every sensor has an intrinsic INL. And I'm actually going to use my laser pointer here. So what INL essentially is the furthest deviation from the perfect output of a sensor. So this graph is showing an angle sensor, and we've got our actual rotor position on the horizontal axis and what the sensor is reporting on the vertical axis. And we're exaggerating a little bit here to show, but for example, let's say this is the actual line. So I've got a motor, for instance, a motor that's traveling 0 to 360 at a constant speed, straight line. Due to latency, what we would see out of the sensor is this dotted line. And so, like I said, that's exaggerated. But due to INL, what we're seeing is the output of the sensor doesn't even follow this straight dotted line. It actually diverges away. And this is what we would call a first harmonic error, because it's got a single positive peak and a single negative peak. And that farthest distance that we get away from that perfect straight line, and again, this is excluding latency, from that perfect straight line is what we consider INL. And I think it's pretty easy then to see how you would have the same thing in a current sensor. If I had a current that was going from 0 to max current, there's no latency necessarily in the current sensor, at least we wouldn't graph it the same way. You would have that same thing. There would be an output that would diverge away from that perfect output, and that would be INL. Misalignment with sensor, and this is specific only to position sensing, will further increase that INL. So there's an intrinsic INL, and then if you misalign the sensor, you can get an INL that diverges even further. And sometimes you get, for instance, if you're off axis, you would get a second harmonic INL. So you get a peak and then a trough and a peak and a trough. But in any case, both of those would be considered INL. And then latency, what I showed here, the difference between the straight line and the dotted line. All of these things can be calibrated out. INL and both intrinsic and due to misalignment can be calibrated in a kind of lookup table. We do some kind of piecewise linearization. We have parts here at MPS that have automatic calibration where you can rotate the angle, rotate the magnet one time, record the actual errors, and then it will populate a table that's in the sensor and calibrate that out. Latency is a little more tricky because you have to know the speed of the rotation to know how to calibrate out the latency. So if you know the time constant latency, the error in degrees will be dependent on the speed of the sensor. And here's an example of our MA600, which actually has latency compensation built in. So if I've got a 10 microsecond latency at 30,000 RPM, that would normally be 1.8 degrees of latency error. But the MA600 can actually, it's got a velocity state variable, and so it can determine how fast the motor is spinning or whatever is spinning. We normally assume a motor, and it will calibrate that immediately back out, so you get a zero degree latency. That can be done on some of our sensors. That can also be done off board on your microcontroller for any generic sensor. So those are the systematic error sources. Random error sources are a little more difficult. They can't be calibrated out because they are random. So you can populate you could populate a calibration table, but the next moment in time, the error source is different. It's random in time. And those are captured by two different specs. So depending on whether we have a position sensor or a current sensor, so this is an MA702, this would be a position sensor. This is an MCS 1806. This is a current sensor. The position sensor captures resolution by it captures noise by effective resolution. So you have an RMS noise, which typical for this type of part, this is a Hall-based part, is 0.02 degrees, which gives an effective resolution of 11.8 degrees. That's essentially the plus minus 3 sigma deviation of the noise. It says, hey, within 99.8% of the time, I can detect a difference in angle that is 11.8 bits. So 2 to the 11.360 divided by 2 to the 11.8, 0.02 degrees. In a current sensor, we capture it a little bit differently, and that's because current sensors don't give a digital output; they give a analog output. And so here we capture it by input referred noise density, the little less intuitive microamps per root hertz. This is a nice spec to at least be able to compare, competitor parts, or compare part A to part B to part C, apples to apples. But I find it, this microamp RMS root hertz is not very intuitive. It doesn't tell me much intuitively about what that error actually looks like. So we can say, okay, hey, here's our input referred at 60 kilohertz bandwidth. That would be equal to 50 milliamps of RMS. Okay, now that makes more sense. If I'm trying to measure 50 amps, I know that my noise is about 1/1000th of my peak measurement. So 50 milliamps RMS. And you can see that's given at 1 nanofarad on the filter pin, which is a 60 kilohertz bandwidth. Like I said, in both of these, whether it's position or angle sensing, we deal with that noise by trying to filter it. Well, you filter it at the cost of dynamic bandwidth. So in engineering, you never get something for free. We can reduce this noise even further, but we reduce the bandwidth of the current sensor, and same with the position sensors. The position sensors have a digital filter built in. Some of them you can program, and you can program that filter to have a larger and larger averaging window, and then you'll find a table somewhere in the data sheet that says, hey, look, for if you want 12 bits or 13 bits or even up to 14 bits, that's fine, you can do it, but your dynamic bandwidth will be very, very limited. Okay, and then we have our third, and really what we're going to be talking about most of the webinar today is the effect of an external magnetic field. Here, you'll see I'm focusing on position sensing. I think it's pretty straightforward for current sensing. For current sensing, that field just biases the Hall effect sensors to the point where it thinks there's more current than there actually is. So if let's say for a current sensor, it's very simple. If I just say, hey, I've got zero current flowing through the current sensor, my output should be zero. But if I've got an external field that's now causing the Hall sensor to give an output, my sensor may say, oh no, I've got 3 amps, 4 amps coming out of the sensor, and that is a 4 amp error. There's in fact 0 amps going into the sensor. It's a little more complex for position sensors because you have to get into a little bit of geometry and some trigonometry, which everybody loves, I know. So let's do that real quick. It's relatively intuitive. We're not going to do any vector math other than a quick visual vector addition. But first, we start out with a position sensor where we've got a target field. And this target field is created by your target magnet. And it's just pointing at, I don't know, what this is, about 45 degrees, something like that. If I've got an interference field now, I've got a permanent magnet from the outside that creates a magnetic field in this direction, which just happens to be the worst case direction. When B interference is orthogonal to B target, that's the worst possible case, right? Because if I have a field that's in the direction of B target, hey, great, I got lucky. The amplitude will change, but we don't care. We're not looking at the amplitude. We're looking at the angle. And in fact, even if I have a external field that's opposite of B target, the angle is still the same. It will reduce the amplitude unless it happens to reduce it to 0, but that's a special case. So we're going to look at the worst case scenario. The worst case scenario is an orthogonal interference field. And when that happens, we're going to do, here's our vector math, but don't worry, it's all visual. Oh, that's not the greatest with my guys up here on top of each other. But anyways, our interference field is going to result in a resultant field, the field that the sensor actually sees of this. Again, we don't care about the amplitude, but we do care about the angle. So now the angle that I wanted, my target field was showing me angle theta, but my target plus interference field is showing me angle alpha. And so alpha minus theta, this part right here is the actual error. And that can be a tricky situation when you're dealing with things where you really care about that angle, and that angle can cause a safety issue if there's an external field. Let's take a look quickly at some examples of field strength and what could cause a high alpha field, let's say. So here's some field strength examples. I'm doing 2 different things, and this works again both for a position sensor or a current sensor, but we're going to put this in the context of position sensing because it's a little less straightforward. But bear with me here for this table. This is just, hey, I've got a neodymium magnet, and my neodymium magnet is going to have a diameter of either 5, 10, or 20 millimeter. And I'm going to assume the height is half the diameter. So here is 5, 2.5, 10, 5, 20, 10. So here's a neodymium magnet. This is going to be a ferrite magnet, which is less field strength, but far more common. Usually your refrigerator magnets are ferrite magnets. And then over here, we're going to look at a current carrying conductor that's close by. And I actually just modeled this by an infinitely long, infinitesimally thin conductor, but this gives at least an order of magnitude of. And then this is the distance away. This is how close we're letting our magnet or our current carrying conductor get to our sensor. All right, so those are all of our variables. And let's take a look at this chart. I get with a small distance, as one would expect, a small distance, I get a pretty large interference. These are numbers in millitesla, which might not mean a whole lot, but I'll put this, like I said, in context in a second. Just to give you an idea, what we're looking for in a position sensor is somewhere between 15 and 50 millitesla for a target field. So if I've got 100 millitesla of interference field, that's real bad. In a current sensor, we're typically looking at a few millitesla being created by the target conductor. And so again, even just 3 or 4 millitesla, even 1 or 2 millitesla of interference is bad. And so if we got something that's close, it's bad. Even 10 millimeters away, pretty bad. 20 millimeters away, we're starting to get into fractional, although if you've got a big enough permanent magnet, still not so good. And at 50 millimeters away, finally, we're pretty safe unless we have a really large, really strong magnet. I told you I'd put this in a little easier context. This is the color-coded chart. Same chart, but now I've converted these millitesla into the actual angle deflection if these were in the worst case direction. And so red is essentially, hey, this is bad, really bad, bad enough that it ruins our sensing. Yellow is less than 3 degrees, which in most applications, we're looking at more like 0.5 to 1 degree of error. So this is still not great, but some applications can handle this amount of deflection. And then green is fractional or 0 degrees of deflection. It's exactly what you would expect. The smaller the magnet, the smaller the current, and the farther away it is, the better off we are. So this is I can't remember how many times I've talked to customers where we've had an interference field from, say, a motor. The stator coils have some leakage flux, and we say, well, let's just try to move the sensor farther away from the motor by a few millimeters, and it works. But that's not always possible, and sometimes you have to have sometimes you have a situation where you cannot move things, or you could have an external motor or an external magnet that could come into the application, and you just cannot afford to have that cause errors. One thing I will say, by the way, for our position sensors, even the position sensors that are non-differential, you can at least tell when that interference field is coming in. We have mag high and mag low. These are essentially diagnostic registers and diagnostic outputs on our sensors. And so if you were to get something like this, where you've got this large deflection, the sensor would at least tell you, hey, something's not right. I'm seeing more field here than I expect to see in the real application. Don't trust the output. So you at least get that, but we want to be able to trust the output. And so the question becomes, how do we protect from these external fields? Well, here's the old way. And I know I'm jumping back and forth between position sensing and current sensing. I apologize for that, but in current sensing, it's always been a little bit easier. And this is the way that we have shunted external fields, the old ways, let's say, and that is you wrap a core around it. So this is, a company that I worked for, my first, I guess it was my second job out of college, LEM. This is their traditional way that they do their current sensors. You have a Hall effect sensor on a die, and you wrap a full closed core that has just a little cutout. And now if you have, and this is the same thing, except it's packaged in here and inside here. In fact, you can even see the little LEM logo on there. In here, this is 3 phases, and each of these will have a closed core. And now if you have an external field, it will essentially shunt that external field through this super high permeability soft magnetic material. It's not perfect because there's this little C-cut in here, but it's pretty darn good. Here's the problem with this. This is expensive. Building one of these closed cores is expensive. These parts, these are, like this 3-phase part, I'm sure this costs more than $10. It's expensive, it's bulky. This works okay for bus bars, but when you're trying to sense a current on a PCB, this is really not a functional solution. And then there's all kinds of things that come along with this. You limit your bandwidth, because if you have a really, really high bandwidth inside this bus bar, it'll create hysteresis losses in this core, and it'll get real hot and melt down. That's no good. So it's not a perfect solution. It's the way that we used to do things. And I say we as in the industry. This is another way, having this so-called large, they call this a shield. This is really the same thing. You could call this a shield. This is essentially the exact same thing, though. This is a core that just has a really large air gap. Because you have the really large air gap, the core can be much thinner because you're not going to saturate nearly as nearly as quickly. The large air gap keeps the flux inside the core down. But it's essentially what it is. It's a core. You have this large air gap, which, like I said, allows you to have less material, but it also means that it doesn't shunt away the external field nearly as efficiently as the closed C core. But this is considered a kind of evolution forward from this because it's less material. You have an IC. It works. It's kind of a pain in the butt. You have to do a bunch of simulations to make sure that you have enough flux, but not too much, that you're shunting the flux from the actual direction that you expect the interference to come from. This works okay if you have 3 straight bus bars right in a row, but if your bus bars in most applications are actually curving around or have turns, it doesn't work nearly as well. And so we get into our differential Hall-based sensing. And now we've got something that works very, very well. We don't add any expense and we don't add any extra space. So let's take a look at how differential sensing works. Again, this one is in the context of current sense. I'll place it in the context of position sense in a second. For a current sensor, the way that most current sensors that are packaged into an IC work is based on Ampere's law. So Ampere's law just says that, hey, anytime you have a current flowing through a conductor, there's an associated magnetic field that is proportional to that current. And you get this old right hand rule. So if your thumb points in the direction of the current, curl the thumb of your right hand, by the way, it's important. Then curl your fingers around and you get your magnetic flux in the direction of your fingers. And so, for example, in our MCS 1806, 1805, this is an SOIC8 sensor. So our SOIC8 sensor has a primary lead frame and a secondary lead frame. They're the same material. I colored them differently here just to show the primary versus the secondary. And what you have is current flowing in through 2 pins on the primary and out through 2 pins on the opposite side of the primary. And as this current flows through, we shape it through this very tiny, we try to get a really high current density right here. And you can see this current then is flowing in the up direction, which means we have a magnetic field curling around based on that right-hand rule. See these little yellow dots? These little yellow dots are Hall sensors. And this Hall sensors on the left side and the Hall sensors on the right side constitute a differential pair. So let's take this and look at it from the side. We're going to flip it like as though I'm grabbing this edge and flipping it and rotating it up. So here we see that primary conductor. The little circles with X's means that the current is flowing into the screen. Our magnetic field then is rotating in the clockwise direction. And the Hall cells on the left side are seeing a magnetic flux pointing upward. And we'll use the convention that that's a positive flux. So positive flux is up, negative flux is down. So B1 sees a positive magnetic flux. B2 sees, by our convention, a negative magnetic flux. And all we do is we say, okay, well, hey, the measurement here is just B1 minus B2. Well, we have positive minus a negative. Positive minus a negative is just 2 times the positive. And so that's our output. Now, if a external field comes in, and that external field is a uniform external field, and it essentially makes both of these guys see a field in the positive direction, well, that field is canceled because it's B1 minus B2. Same thing. If that external field comes in and shows both of these guys in the negative direction, then it's canceled. It'd be minus B1 minus B2. Canceled out. And so this is differential sensing for current sense. It's a simple concept. You are looking at each side of the conductor, and each side you expect to see an equal and opposite magnetic flux. In position sensing, we have kind of the same thing. Now, typically in a position sensor, what we're looking at is the magnetic flux in the horizontal direction, let's say. So let's say this is our target magnet, and here's our target magnet in 2D. We have magnetic flux coming out of the north, going into the south. And if we placed our sensor right here, we would see this magnetic flux pointing to the right. And as this thing rotated, and it's hard to picture a rotation here, it would be like south going into the screen and north coming out of the screen. You would see this flux then start to point into the screen until it was reversed with south over here, north over here, it'd be left. And so you can see how as it would rotate, our magnetic flux would rotate into the screen left, out of the screen right. That's typically what we're looking at in a non-differential position sensor. We would have a special Hall cell called a vertical Hall cell. In other words, a Hall cell that's sensitive in that direction. So let's say the die would be like this. We would have a Hall cell that's sensitive in the direction of the die. But we can do the same thing by looking at two parts of the vertical field. So instead of looking at the horizontal field, now we're going to take two sensors. We're going to put one over here and one over here. And here we see a magnetic field pointing upward. Here we see a magnetic field pointing downward. And hey, it's kind of reminiscent of that current sensor. We have a differential pair. The difference is we need to have at least two differential pairs because we need to know as this magnet rotates where we're seeing the maximum flux and where we're seeing the minimum flux. And so here, let's take a look down here in 3D. This will be much more intuitive. In 3D, here we've got the die. Here we've got our two differential pairs. They're diagonal from each other. And here's our magnet, and we've got the magnet mapped in X and Y. This is just geometrically mapped. The Z is what is the actual flux in the Z direction. So over here, remember our convention for magnetic field is that magnetic field comes out of the north, down and into the south, up, just like we had. So this is actually backwards from here. I didn't even realize that until just now, but here we have the north on the right side, south on the left side. The flux comes down, so you get a negative flux here, comes back up, you get a positive flux here, and that's how you see this map. Imagine now as this magnet rotates, you will see this entire map rotate, and so you'll see these maximum flux rotate from BZ2 to BZ3 to BZ4 to BZ1 to BZ2. And based on that differential pairing, we can determine the direction. If I have a uniform magnetic field that comes in, an external aggressor field that comes in and shifts this entire curve up, it doesn't matter. That's fine. The difference between Z2 and Z4 remains the same, and the difference between BZ1 and Z3 remains the same. Same thing if it shifts down, doesn't matter. The entire thing will be shifted. And so that is how differential cancels out external fields. Now, I'm going to revisit this for 1 second because there's one important caveat here. And that is, because I've got B1 minus B2, and I've talked about shifting everything up and shifting everything down based on a uniform field, what happens if I have a field with a gradient, which especially in a current sensor can be an issue, because as you have this current, and I didn't draw it here, but you have this magnetic field. This magnetic field, as you go away from the current carrying conductor, decreases with the cube of the distance. And so it gets weaker and weaker and weaker. And so, and it's a pretty large gradient. And so a lot of times in a current, if you have an external current that would be causing a field here, this field is not going to be truly uniform between sensing point 1 and 2. There's actually a gradient. In other words, let's say the field is pointing upward. It would, point 1 would see an upward and point 2 would see an upward or a positive magnetic field, but maybe B1 sees an even stronger field. So the amplitude is higher here than it is here. That can cause an issue because there's still a difference now. B1 minus B2 has an actual value. And so when the field is not uniform, when there's a so-called gradient, this doesn't completely reject the field. But we have a solution for that too. And that is to use 3 sensors. And now we can use sense point 1, 2, and 3, and this will reject even a gradient field. How does this work? Okay. Let's take a look here. I chose these 2 sensors. It's our little QFN sensor and this goofy package, which name I can't even remember. And I chose these on purpose because here we've got current in comes around this kind of half loop, current out, same thing, current in, half loop, current out. I chose these because you can see the conductor on the outside of the package. If we place one Hall sensor here, one in the middle, and one here, so same thing here, up here, 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 we have one primary conductor that's going into the screen and then loops around, and this conductor comes out of the screen. We get a magnetic field rotating clockwise around this conductor, counterclockwise around this conductor, and essentially we will see double flux on B2, a kind of single flux on B1, which it looks like I forgot to label, but sensing point 1, and sensing point B3. So B1, B2, B3. I can see I screwed up these labels. That's my apologies. We now take, for the measurement, we're going to take 2B1, I'm sorry, 2B2, because it has double the flux, minus B1, minus B3. So 2B2 minus B1 minus B3, and that is our measure. Again, let's take a look. B2 in this case is negative. B1 is positive. B3 is positive. So 2B2, which would be a negative number here, minus a negative, minus a positive means you would have a fully negative actual value here. If all of these get increased by a uniform field, no problem, they get canceled out. But importantly, if they get changed by a first order gradient field, B1 and B3 together will average. So assume your field is, let's say, low, medium, high. The gradient looks like this. B2, this is B3. I hate this label. I apologize. B3 and B1 together will equal B2. So you still have 2B2 minus B1 minus B3. These two together will average to this, and it cancels out. So even a first order gradient is canceled out in either direction. This is something that we're starting to integrate into a lot of our current sensors, because if we want to pack, especially, you can imagine in these little QFN package and this little goofy package that I've got to remember the name of. The idea is we're putting these on PCBs where people are trying to pack 3 phases of current in very, very close together. We want to be able to kill not only the other phases uniform field, but the gradient field caused by the other phases. All right, so let's take a look at an example, and we'll do, again, one position sense sample, one current sense sample. The position sense example that I chose is because I've dealt with this many, many times. It's electronic power steering. You have an electronic power steering, you generally have 2 places where you put a position sensor. One is the torque sensor that senses the driver input, and one is the actual power steering motor gearbox that feeds back the position of the motor. We have these parts it's an ASIL D And for those of you not in the automotive world, ACLD means that if something were to go wrong and one of your sensors were to output the wrong information, someone could die. And I think it's pretty straightforward to see how that could happen in steering. What we don't want to happen is we're driving along and your passenger hands you a birthday present, which is a nice big neodymium magnet, just what you've always wanted. And your car then veers off the road and off a cliff, ruining your birthday. And you never got to enjoy your beautiful, nice neodymium magnet. That can't happen. So this is an ACLD application. And so we use a differential part so that if someone hands you your nice your birthday present that you've always wanted, I know you guys are like me, you love neodymium magnets, and you want to have your time to enjoy it. So even when you bring that neodymium magnet near, the differential sensor rejects it, and your car continues down the road, and you get to spend many, many years with your beloved large neodymium magnet that you got for your birthday. It's a specific example, I know. In current sensing, it is quite the same, except that instead of a permanent magnet, normally we're seeing interference from other phases. So here's a very typical current sense application. We've got a high voltage bus and 6 switches. So we've got our 3 phases here. I think I have these as IGBTs. They could be MOSFETs anymore. I think they're like GaN FETs a lot of the time. In any case, each phase has an isolated current sensor put on there. And what we don't want is that phase 1, which does create magnetic flux, as we know, interferes with the sensor on phase 2, and phase 2 doesn't interfere with phase 3, and poor phase 2 is getting it from both 1 and 3. And so we have to be able to reject these fields. Now, there's ways to do that geometrically. You can just design your PCB so that it's huge and your current carrying traces are on opposite ends of the PCB, but that's not practical. The better way is to just make sure that your current sensors have differential sensing pairs in there. And now you can put the same current sensor on all 3 phases and don't have to worry about interference. Oh, I forgot to put a little animation. Yeah, there's our magnetic field interference. So the visual reminder that this guy's just radiating out a magnetic field, and we don't want this guy to have to deal with that. Oh man, it's even animated. Look at that. It's a big radiation. So the differential becomes even more important. Thanks, guys. That is my presentation on differential sensing. Check out our solutions at monolithicpower.com. We've got our sensor solutions catalog, and I will take a look and see if we have any questions. If I can figure out how to do that on Zoom. Let's see here. Q&A. There we go. Why not estimate gradient error with measurement dB B1 plus B2, which in strong gradient field returns the error value and the correct output accordingly? Oh, interesting. Okay, so I've got a question. This is a pretty technical question, and I have to think through it here. Someone asked, and it's anonymous attendee. Someone asked, why not estimate the gradient error with measurement B1 plus B2, which in a strong gradient field returns the error value true, and can then correct the output by B1 minus B2 minus B1 plus B2. So I think on first, and I'm gonna have to look at this, but I think on first glance at this, the reason that cannot be done, and it's possible that it can be, and I'm just not thinking through it properly, but I believe the reason that we can't do that is that then you would affect the measurement of the target field. But I got to think through this. I'll tell you what, I will. Well, it's anonymous. If you want to, anonymous attendee, if you want to throw your email address in the Q&A, I will answer that via email, and I'll think through it. Why was differential technology not used earlier, as is obviously very capable? Okay, thanks, Anonymous. I got your email address, and I will send you that answer as I look through it. Why is differential technology not used earlier, as is obviously very capable? This is true. And I think, I've actually thought about this before. I think this is a situation where this seems like a pretty obvious answer, or it seems like a relatively straightforward solution to a problem. But it's one of these things, many times in engineering, I've found what seems like an obvious and intuitive solution is an obvious intuitive solution once you've seen it. And my only guess here is that it hadn't been really thought of, or it had been thought of as too complex, and no one had seen what seems to be a relatively straightforward and obvious answer, because we've been so focused on things like shielding and magnetic cores. And this was just something, I remember a product that I worked on, again, this is years and years ago, when I worked at LEM, which was kind of a first attempt at a non-core based current sensor. And it went onto a PCB, and it was so sensitive that we even had problems with earth magnetic field causing offsets. And it just never crossed my mind. And I like to think that I'm somewhat creative and intelligent. Just never crossed my mind that, oh, hey, this would be simple. All we need to do is add another Hall cell, which doesn't even take up that much die space. And so I think that's the answer to your question. I can't say for sure, but I believe the answer is simply that it's one of those things that that is obvious in hindsight. Ryan says, please consider adding scent output to your 3D sensors. Aha. This is not the first time I've heard this, so I really appreciate that kind of feedback. What is that? It's single edge nibble transmission, I believe. And for the automotive guys, I've heard this before, and this is something that we are in fact working on. I don't know if we're working on it in the context of the 3D sensors, but we do have position sensors that we're working on with scent. And Ryan, if you would consider sending me an email with a little more detail on your application, I will get you also a roadmap of what we're doing. And then also that helps me put in context, exactly which applications. It seems to be, at least in my experience, that it's automotive and that it's safety critical applications where people really like the scent protocol. But certainly I'd love to have a further discussion on that. There says, if you'll send some response to a question, please add me. Oh, okay, so Darius, no problem. I will also add you on the question about the other potential way to do gradient rejection with two Hall cells. I'll add you, and anybody else, if you're interested in being on that email, go ahead and throw your email in the Q&A, and I will make sure that I include you on the response once I think it through. Andy says, are you considering adding field strength indication to sensors like MA600? Yeah. So Andy, we are. This is something that we went to. So the differentiator on the MA600 and some of our other parts is that the MA600 is TMR based. And so we do, and I'm trying to think if I've done a webinar. You may be able to go through and find a webinar, or at least an article written by me on spin axis and how it works. But our parts, our position sensors, because we use the so-called spin axis and it uses time to digital conversion, we don't get a good source of magnetic field strength like you normally would with parts that use like arctangent and D to A converters. We don't have a D to A converter, or I'm sorry, an A to D converter. We don't have an A to D converter in our sensor. But there is a part of the signal where we can at least estimate field strength, even in the MA600. And we will do, and we've done this now for a couple customers, we'll do a semi-custom part where we make that analog output available. It's essentially I want to say it's a PWM. I have to look at it again. It might be I remember it's a 10 kilohertz signal, but we can make that available. And so if you drop me an email, I will send you that data sheet that has that. And again, it's rough field strength indication. It's within like plus minus 10 millitesla, I want to say, but I'll get you details on it if you send me an email. Please comment on new AMR, TMR sensors. Certainly. So at MPS, we are using TMR technology. So our evolution from Hall is towards TMR. AMR we've looked at, and yeah, I mean, AMR is certainly a viable technology. Based on the noise profile and the environmental characteristics, so far we've chosen TMR as our kind of next gen sensor. Now, the trade-off with TMR is that it's not a standard silicon process. So right out of the gate, it's a little more expensive because we can't just put it through a normal process. We have to do a post-process. That being said, the advantages are pretty prolific. So in a position sensor, for example, the MA600 that was mentioned before is a TMR-based sensor. It has a 0.5 degree over temperature INL. So that's compared to a Hall sensor, which is about double, possibly even slightly more than that. The noise profile on a TMR allows us to have a high resolution, so the same resolution as in one of our Hall cells, except with well, let's put it this, I'll put it the other way. Normally, like I said, in Hall sensors, you have this trade-off of bandwidth per resolution. We can have the same bandwidth as our Hall sensor with 3 extra bits of resolution in a TMR, and that's a big deal. I showed an example that was 12-bit and a Hall sensor, and the reason that that's kind of our standard is that 12 bits is what you can get and still close the loop on a motor control feedback with a Hall sensor. With TMR, you can get to about 15 bits and still have enough bandwidth to close the loop on motor control. So there's definitely some advantages. The same with current sense. And current sense, accuracy gets better, bandwidth gets much higher. If you want to get into the 1.5 megahertz and up type bandwidths on current sensors, it's almost certainly going to be TMR. But the expense is there. And when I say the expense, figure at least a 50% cost adder right now until we find a better way or a better process. All right, I got some people say, add me in your response. No problem. I certainly will for everybody that sent me the email address. James, will the slides be available somewhere? Yes. The slides will be sent out via PDF within a couple days, and the entire presentation, including a recording, will be available on monolithicpower.com in our education section eventually. I think they'll also send you a link to it when they send you the PDFs. Are there position sensors from MPS which allow ASIL D with single output and single die? Yeah. So our MAQ, MAQ 7. Let me find the part number. Yes. So we are working on that. Essentially, it's difficult to do ASIL D with a single die, and this really has the system has to be ASIL D, and so it's up to the safety engineer at the end customer to determine what their real requirements are. But we have parts that are made for that application, made for ASIL D application. MAQ 74. Why can I not think of the part number? I'm going to actually cheat for a second and find it. I don't know why I can't. Oh, in fact, you know what I can do? It was in one of my slides. Give me 1 second. My brain is crying out on me. Here we go. We'll go back. It is this part here. MAQ 79010. 79010. So this is the part that's going to be designed to be ASIL D. Today, I've got customers that are using it in ASIL D applications, but they're actually using 2 parts. This is a single die, by the way, but they're using 2 parts, and you put these parts essentially one on each side of the board, and so they sense basically the same field. I think that it's possible to use this part as a single die, single IC solution with the amount of diagnostics that we have in there. But that's kind of up to the engineer. And oh yeah, and yeah, I know you. Yeah. I got your email. Gotcha. Field service like an indication. Yep. All right. Position sensors for the PS. Okay. So yes. So this is our ASLD. Andy, I do have your email. Neodymium. Is a neodymium magnet a must to run the differential Hall sensors? No, it is not. You can have any dipole magnet. You don't have to have field strength is not the goal. So you can use powdered ferrite as long as you can get plus minus 10 millitesla, and we'd really like to see more like plus minus 20 millitesla. Then you're fine. And what will happen is that if you go from 20 to 10, is your resolution will drop. So, but any magnet that's dipole and that you can get that much field, and the other two variables are, in terms of magnetic field strength at the sensor, one of the variables is the magnet material. So neodymium is the strongest, but the magnet size and the air gap between the magnet and the sensor, and it's not difficult to get a ferrite magnet to close enough to provide enough field. Is it possible to get straight field robust with TMR as well? Absolutely. Yep. With TMR, you do the same thing. You just have two elements that are placed in the just like the Hall, and yes, it is possible to get that same straight field robustness. You just do the same differential technique. It is technology agnostic. And then you have mentioned the immediate latency correction of the position sensor. Is it working principle kind of continuous loop monitoring the speed from the position corrected the output in real time? Yes, it is. For our MA600, which is that part that I talked about that is that has the zero latency. Essentially, so I talked about the resolution filter, the noise filter in the sensor. That filter is built with a position state variable and a velocity state variable. And so it becomes almost, I would compare it to a Kalman filter. It's not a true Kalman filter, but you can compare it to that. And it essentially uses the velocity state variable to estimate the speed and then correct the position based on the speed and the known latency, if that makes sense. And that, I believe, is the end of the questions. Hey, guys, I really, really appreciate and I love all the questions. That makes these so much more engaging and dynamic. So thanks, everybody, for joining. Thanks for paying attention and asking great questions. And I'm going to put my email address up here again. I think hopefully everyone had a chance to write it down or take a look at it. But any other questions or anything, comments, anything like that, please feel free to email me. And I will get everybody who left their email address the answer to the first question that was that's interesting and I need to actually think through. I will get everybody a result there. Other than that, thank you, and I will see you guys next time on our next webinar.